Okay, so people are back. I guess a lot of projects to hand in. So what I'm going to do then, I'm going to try to take a quick recap of what we did on Friday. It's Tuesday today, yes. So I started to present the spectral element method, which is a variation of the finite element method. So what's the difference between the finite element and finite difference methods? Well, finite difference methods, they have a finite difference between each of the elements, so the elements are regular, like so, like the project you have implemented. Whereas in, well, a very general finite element, so then the elements can be any shape you want. Meaning that, for instance, compared to the adaptive quadrature we had a different length of our intervals depending on how much the function was changing. So this is an instance for, well, I mean, if you want more accuracy in this region, we can just improve or increase the amount of elements in this region. For instance, if we are very interested in this region, or if a lot of stuff is happening in that region. So it's like a brief overview of everything. So in order to actually use the spectral element method and talk about it in a meaningful way, we introduce the 1D scalar wave equation as scalar wave. And it's going to look a bit different than what you had. This is the density, which is dependent on, well, I can should. So this is dependent on position. Then you have the double time derivative of the displacement, u, which is a function of x and t. Then minus the partial spatial derivative of the elastic parameter mu, again a spatial dependency, and then the x of the displacement u of x t equals a function like a driving force. For instance, inserting the source as you did in the project. Well, 8 groups of you, or was it 6? Then we applied Newman boundary conditions, which means that, oh, I guess I should do it properly. So the boundary conditions states that the derivative at the end, so x equals 0, and the xu at 0, so it's still for the end. So the main now is this, so 0 from L, displacement could be a string going up and down here, and it should say still at the endpoints. And we also have the initial conditions that the string should be flat when we start, meaning that u of t equals 0 of t, well, time derivative 0. So this is the initial condition. I mean, I'm just going to do a very quick recap since I actually taped the last lecture and you can see it there. Yes. What we did next was to find the weak formulation of this equation by multiplying it with a so-called test function we called w, and then integrating it over time. No, over space, sorry. So what we get when we integrate this over space and introducing a test function w, test func. So we quarter domain G. So G equals 0 to, now just stop me if I'm going too quick now. I'm just trying to summarize everything. So the integral over this G, which is our interval from 0 to L, W, which is a function dependent on space. As I should write it explicitly. And then the density is still of space, space length, space and time. Minus dx mu dx mu dx equal to w f, well, like so. So this is basically the 1D scale wave equation, only that we've multiplied with a test function w and integrated it over, so w and integrated over space, like all space. This is just 1D, so well, it's just a simple integral, like so. What we did next was we used integration by parts and the boundary conditions to get an easier form, so we don't have the spatial derivative of this elastic coefficient. So we can actually write this on the form g rho mu w dx plus m g w, oh, sorry, mu first, spatial of w dx x w dx. So then we've integrated this bit over parts, and then we see that we can cancel some parts. So next we introduced Galerkin projection, and I'm pronouncing this wrong. It's a Russian name, but Galerkin, something like this, which means that we do a well, basis expansion of this displacement u. So projection, which is x of t, is then the sum I equals 1 to n, so this depends on how many basis functions we have, where we have coefficients which are dependent on time, and basis functions which are dependent on space. Like so, and this is approximately equal the real displacement u of xt. And how good this approximation is depends on, well, the parameters and how many basis functions we use. If you use an infinite amount of basis function, well, then we will get the exact same function, but then again we are going to use an infinite amount of basis functions, and we don't have space for them in the computer. So I have to stop somewhere. Yes, and then we can insert this Galerkin projection into the weak form of the wave equation and say that the projection should also solve this equation. So then we have added another step of abstraction to our spectral element method. This again should then hold for all of the basis functions psi, or psi I. Yes, I'll skip this bit. And then, since this is a 1D equation, we have a 1D domain, which we will divide into or partition into NE disjoint elements, and they can have a length as well, the length we want. So from 0 to L, green. So we are going to partition this. So G1, G2, G3, G4, G5, and G6. So in this we have 6 elements, and they can be of a different size. So each of these elements will, well, if you look at G1, we'll say that it starts from A and ends at B for each of the elements. Just, I mean, you can have A1, B1 is G1, and then for G2 you can have A2 and B2 and so on, if that's easier to make sense of. The only thing required of this partition is that each of the elements are disjoint, meaning that they don't overlap, and the union of all the elements is the full interval, or the full space we're working on. In mathematical terms, that means that, well, the union of Gi equals 1 and E should be big G, and Gi intersected with Gj should be the empty set, as long as I is not the same as J. That's from all I am. Again. Then we're getting speed. Next, we try to solve this wave form of the wave equation on each of these disjoint elements. Yes. So this is going to be a bit skip, but it's going to be important later. Any questions before I rush on?
What you refer to the form is that without the boundary condition.
That's also with the boundary conditions. So I forgot to mention that the boundary conditions are kind of baked into the weak form, if you look at it. So, but this weak solution for each of, well, for the full domain we have now, and using the Galerkin projection, we will get equals 1, and I've also done some more steps here, so I'll try to explain them after I've written the equation. So now you see we have to sum over all of the elements, these G elements. Do an integral again. Rho C J C I. So this is the first thing also that I've, instead of using this test function W, well, I'm still using this test function W, instead of using this W, I'm using the same basis functions as for the Galerkin projection. And this will make stuff a lot easier later on. So why can I use the basis function of the Galerkin projection? That's because I can use every test function I want. So then I'm just gonna pick something I already have, which, as you will see later, makes sense. So that's the first term. One and T is nope. Don't forget that. T again, sum over all the elements. Mu x, c, j, x, c, I, dx, and again, S1 and E, an integral over the full domain, over each of the domains by themselves, Cj and dx, like so. So, in this formulation, we need to integrate, well, these coefficients, ui, from the projection, depend on, well, the full integral. So then you have to integrate, well, the full domain, so you need to know the answer in all of the domains before you can actually determine these coefficients. So what you do then is you can pick basis functions that only has support on one of the elements. Meaning that if a basis function has support on this G4, then this is the only element where it is non-zero. So on G3, then it's going to be 0, G1, it's just 0, and G6, just 1, 0. So that means you can actually filter out the influence from just one of the G elements of the full G domain. Now I'm always this. So then we did this, and then we introduced a reference element. So yep. So when we introduce the spaces function that only have support on one of the elements, we can solve for only one of the elements at a time. So that is what we're going to do, continuing on now for some while. So now I'm going to introduce CIE. One ELT, one element. So again, this Galerkin projection at one of the elements. T, oops. X is inside the element GE, so E are going to be 1, 2, 3, 4, 5, 6, depending on that one over there. We have n plus 1 of these basis functions, and again we have temporal exponential coefficients ui e, because it's only from the element number e, and from the basis function ci e, which only has support on this g element. Questions? Yeah.
So this approximation, like you assume that the value can be separated in time and space, like separately.
Yes, this is an assumption. If it holds true, well, maybe, hopefully it will. In this case, it will hold up to a certain degree. So it will be a good approximation, especially if you let this run to infinity. So yeah, maybe you remember from when you solved partial differential equations and you could actually separate them in order to get a solution. You do get some solutions for them, but there could be some solutions that depend on some kind of combination of t and x, or time and space, such that you can't express it in this way. That is a possibility, but in this case, it's not going to happen. I don't quite know the mathematical proof bits, but I've just assumed that this is true. This holds true. So yes, continuing on, we will rewrite this a bit because this is for all of the elements. Since we are summarizing over all of the elements. Oops. One I double dot E to the integral only over this element G now. Again, density is dependent on space, but I'm neglecting to write it to save some time and joke. Plus 1 and plus 1 Q I E, again temporal. G E mu dx C J E dx C I E dx E C O J E and F dx. So this is the weak form on only one of the elements. And something you can note yourself is that the total amount of basis functions now is NE times n plus 1. Because each of these elements E has n plus 1 basis functions. You could, in principle, have different amount of basis function for each element, but then you have to actually make sure that you actually do have different basis elements on each. Now, basis functions on each that has support on each element, but it just complicates matters. So that's why we say that we have n plus 1 basis functions that have support on element, for instance, G5, and the same amount on G3 and G6. So that's why we get this amount of basis functions. And then we had the reference element. So when you have this expression for each of the elements, and all of the elements can have a different length, then you have to solve a lot of different integrals. So what we can do, we can just stretch or squeeze this GE reference element so that it fits, no, not reference element, we can stretch or squeeze this GE element such that it fits with a reference element. And then we know how to integrate on this reference element. I'll do this here, I think. So we are going to call this reference element big lambda, or capital lambda, such that we now have, let me get the arrow straight. So now we have an element AE, BE, for the element GE, and then we have a reference element big lambda, going from -1 to 1, and then we want a transfer function on transformation FE, going this way, and then you have inverse function going the other way. And then to keep to separate these better, we say that on the reference element we have xi, and on this g we have the regular space x. And this xi is just a linear stretching of x. Then I think one of the last things we did last time was to actually define this function fe as, for this transfer, cfe of xi equals a e over 2 times xi plus be 2 1 plus xi. And then we can apply this transformation on our solution for one element, and then we'll get kind of a reference solution. Let's see. So
The
next,
transformation can be nonlinear.
no,
It has to be.
yeah, it should be a linear transformation. It has to be, yeah, it has to be bijective. And it has to have a good inverse as well. So a bijective transformation means that you are able to hit every point in both of the spaces, and well, each of the points are mapped to different points. If that makes sense. You should be able to go, I mean, if you are over here, you should find a corresponding point here, and every point should have a corresponding point up there, and also the inverse. So you shouldn't be in the case where one point here is mapping to either this point or this point, and that 2 points in big lambda can map to GE. Then you're into trouble. So it has to be a linear transform. I am pretty sure it has to be a linear transform. There could be some kind of higher order transforms that do work, but linear transforms, well, work. Yes. What was I going to do? I had this and then 7s. So yes, now we apply this transformation Fe on the weak form of the 1D solution. And then we get a well, nice equation. Plus 1 plus 1 e. So instead of having the integral over the element GE, I have it from -1 to 1, then rho of all of these x's transformed to j e x I e x psi x psi, just so we are integrating over the correct variable. I plus 1 plus 1 e minus 1 to 1 mu psi to psi j e psi transformed coordinates d psi e x psi squared dx equals d psi x psi, yes. And then the source through -1 to 1 c j e x X psi psi d psi. So this is the general weak formulation on each element. It might look like black magic, but most of this should make sense. I explained it in further detail in the last lecture, how to actually get this formula. But I mean, it just looks complicated because you have all of these. So if you now try to discard those, then you see it looks a lot easier. And then all of these extra derivatives is basically because you're changing the from variable x to xi. And then we return to these basis functions again. So which basis functions do you think are good to use? Second? Yes, that is what we're going to use. So we're going to use Lagrange polynomials. So we choose the n plus 1 Lagrange polynomials of degree, n, for each of these elements. And then we introduced something called Gauss-Lobato-Legendre points, which are slightly different from the Gauss-Legendre points we had earlier. And to get these points, I suggest you try to look up a table. I wrote them up last time, but yeah, they are complicated. Or not complicated. I mean, they look complicated. So we're going to use n plus 1 for this, n plus 1 for each of these. So now we're only on one element. So for this element we want to use n plus 1. Degree n. Let's I'm going to write this in full. Gauss Lobato or GLL points as collocation points. And now if we wanted to use these Lagrange polynomials for an arbitrary element GE without performing this transform, then we had to actually calculate these collocation points for each of the elements. So then it's actually a lot easier to have these collocation points pre-computed for our reference elements and then just apply a linear transform, which is a fairly cheap computational thing to do. So now we are going to introduce these instead of Ci of x xi, we are going to say Li n of xi, where this xi is from -1 to 1. Shouldn't come as a shock, since that's big lambda is defined from -1 to 1. And that is where these live. So I think actually the appendix of this full waveform inversion book by Andreas Fitchner, he has a table over these GLL points, if you are interested. And also some good reasons why to have these GLL points is that I suppress this ringus phenomena, which we had earlier with these, well, ringings at the ends of the interpolation points, or no, the things we're trying to interpolate. If you remember. And also it's been shown that picking these GLL points, you can actually reduce the numerical inaccuracies. And we can use them for integration. So we can use, well, GLL quadrature, meaning that we can solve this integral fairly easy. See which time is it? Yep. So if we then look at this advanced looking equation, if I introduce this Li, I'm going to just drop right this n all of the time. Well, the degree of it, this n. Then we'll see how this equation looks. And it's going to look fairly similar to the one I just erased. So again, there's sum 1 plus 1 and E double dot times T that's 1 to 1, and then I'm going to introduce a row bar of xi Lj of xi. I'll come back to what this means. The row bar is nothing magical or anything. Just a reformulation of the problem. One mu bar xi xi Lj xi. If you don't want to write this xi a lot, this is kind of a complicated character, then just pick something else, as long as you are consistent. Squared psi j of psi f bar of psi t dx d psi. So this is basically the same equation here, where we have changed these psi's, or psi's, I guess, psi's into the li's, and we've created a shorthand form of this f of, well, let's do this again, rho of x of xi. So this means rho bar of xi is the same as rho of x psi mu bar psi is mu. So kind of the transformed density and elasticity and, well, force. And then I promised we are going to introduce GLL quadrature. I assume you all remember this from a couple of lectures ago. This means, see, we're going to approximate the integral with a sum when we evaluate it at certain points. So this, let's see, minus 1 to 1. So g here is just an arbitrary function. Dx, we approximate this way. This one, so kind of weight omega I, g I, where these weights can be pre-computed. Minus 1, Li, polynomial. Let's get this. So I mean, we're still solving integrals, but these can be pre-computed. This is just a number. Now we're using the GLL points, so this is called GLL quadrature. So what do you think happens when we introduce this approximation into our integral? Well, it becomes a lot easier. But before we do this, let's also try to do an approximation of the derivative. As you see here, we actually need to figure out the derivative of all of these Legendre polynomials. Lagrange polynomials as well, not Legendre. Lagrange polynomials as well. But I think before we do that, we have a 15-minute break. Unless there are questions. No?